Marco Gaboardi from the University of Buffalo is going to tell us about how to build differentially private algorithms effectively and with guarantees that they actually do what you're expecting. So.
Thank you. All right. So thanks, first of all, to the organizer for having me here. It's a pleasure to speak here, and I hope I will show you something interesting during these 3 hours. So I think I'm the only person here, or maybe not. I see other people that do a bit of formal methods, but we are very few of us. But I think formal methods are very important for what we are trying to do, for trying to build a correct application that respect privacy. And I'm happy to be here and present some of our work. So John recommended me to prepare a mini course, not only a tutorial, so I tried to structure my 3 hour in a kind of mini course. And the idea is the one you see here. So in the first part, I will give you an introduction to formal methods. I'm not sure if everybody knows what formal methods are, or maybe you just have a rough idea. I want to give some common vocabulary, some common understanding of what formal methods are and why they can be useful in this setting. And then I will focus on one particular kind of application that people have developed in terms of languages and systems supporting differential privacy. While in the second part, I will focus more on formal verification, which is the idea of proving our implementation correct. So in the first part, I will focus more on support for differential privacy, while in the second part, more proving that our application are correct. And then I will try to finish in the third part with some other direction that people are looking at. And also trying to give you some pointer for some potential interesting questions that we can discuss during the semester. I think for me, the ideal would be to have some of you bring your own expertise and try to help with formal methods, or vice versa, trying to use formal methods for some problem you are interested into, and so have some interaction during the semester. All right. So one thing that I should mention before starting is that I will not show you many mathematical formulas, because this is not what we do, but I will show you a lot of code. So I will try to walk through the code slowly, but I think it's important if the code is not clear that you stop me and we try to understand it better. The code will be quite simple, not too complex code, but I will have a lot of examples, so I think it's important really that we make this a bit interactive. All right, so let me start with a brief high-level introduction of what formal methods are. So the general idea is always difficult to introduce a big area like formal methods, but the general idea I think that we can have about formal methods is that we usually face the problem of design our algorithm, and we prove that this algorithm has some good properties, but at the end of the day, we need to have this algorithm implemented in some system or language that can do the job. Like as Cynthia was mentioning, the census is going through the effort to implement a theory that we know into a practical application, and we in general want to have some guarantee that this is done in a good way, and formal methods try to make this process as mathematically rigorous as possible. So it's a collection of technique to take an idea and bring it to an implementation in a mathematically rigorous way. So in other term, what is the goal of formal method is building applications that are correct, giving you some confidence that what is implemented is correct. Now, why correctness matters? I hope I don't have to make this too explicit here, but in general, we want to have correctness because we want to avoid critical failure. We don't want that we implemented all our application and then we don't have the property that we expect. This has happened in many situations, from financial system to self-driving car to, as I put here, some rocket that had some software problem and this created some failure. And we don't want this to happen also for differential privacy. We don't want that something that we claim is differentially private in the end is not. Now, what do we mean by correct? I think this is one of the main issues that often we face when we try to interact with people outside our field. So it's very important for us make clear what the notion of correctness means. For instance, we are interested in differential privacy, and this is a mathematical formulation of what we expect from our algorithm, and this is a formal enough definition. In general, we interpret this kind of requirement as specification that our system have to meet. And we have two kinds of specification in general. One that we call usually functional specification, that is more about what is computed, and another kind of specification which consider non-functional aspect, how this is computed. For instance, we may, in application, for instance, to autonomous vehicle, we may want to have some strict requirement in terms of reaction to some action. Now, the problem is that what correctness means is not only is not always easy to formalize. So if we take again some application like the one that nowadays are hot, like autonomous driving, or like some software for recognition and so on. What do we mean here by correctness? It's difficult to formalize the notion itself of correctness, and this is why people often relies not on formal methods, but more on some empirical evaluation of correctness. So I want to distinguish this situation from what we are trying to address. What we try to address is a situation where we can specify what our program is supposed to do, in contrast with just doing some empirical evaluation. Now, last slide to try to convince you why correctness is important. I want to mention one project that was I think quite successful in showing the usefulness of formal methods. So DARPA had a challenge for trying to protect a drone from hacking. It was a challenge where they were asking to some team to hack some drone. And before the original drone was easy hackable, so a group of hackers were able to enter the system and take control of the drone quite quickly. But then the challenge was to improve this system and avoid further hacking. And a team from the formal method side fully formalized the main part of the software that the drone uses, and as a result, the team of hacker was not able to access the drone software anymore. Now, this is not, of course, a mathematical proof. This is more of an empirical proof. But I think it tells us something. It tells us that if we pay attention on how we design our application, how we make sure that they satisfy some property, we can guarantee the absence of some bugs that usually are what we can exploit, for instance, in security application. Okay, any question on the general picture? All right, now, I say that correctness is important, but is correctness easy to determine in general? Because maybe it's easy to determine, and maybe we are trying to develop tools that are not useful, and maybe I'm just wasting your time with this. So let me try a small test. Is this simple program correct? So I hope the program is self-explanatory. It's a basic program. Let me try to read it. I use a kind of pseudocode. I think most of you should be familiar with something like this. So it's a function that has a variable r, which is initialized to 0, then a variable n, which is initialized with one of the parameter y, and then it loops until n get to 0, and it does r equal to r plus 1, and n equal to n minus 1, and then return r. Yes?
No.
No, good. It's not. Otherwise, I would not show it. Why is not?
We don't know, actually, because there's no spec.
That's exactly one of the important points. We don't know, actually, if it is correct or not. But something went wrong here.
There's definitely something fishy going on.
Yeah, something fishy is going on. And why something fishy is going on? Because this function is called add, so we expect that the programmer wanted to implement an addition function. But then the variable r, which is the one that in the end we return, is initialized to 0. And if we look at the loop here, we just increment it, and we increment it mainly accordingly to y. So the result is just y. So something seems wrong, but as one of you pointed out, what is wrong here? Is the name or the program? Right? And the solution is what you suggested, and is we need to give the specification and say what we want to compute. Now, this, of course, is a simple program, and let's assume that the specification is what the name suggests, so that this function should compute the addition. Now, unfortunately, just adding this condition is still not enough. Why is not enough? What can go wrong?
We need conditions on x and y, for
We
instance.
need condition on x and y, exactly. Because otherwise, for instance, we may give a negative number and never hit 0, and so this program would run forever. Okay. This is dangerous. The button for next slide is close to the one for exiting the presentation. I will try to avoid doing this more. So we can add also a precondition. Usually we call them precondition and postcondition. A precondition that tells us what we expect from the input, and if we don't meet this precondition, we don't run the program at all, because it's a kind of contract that we expect with that an interface that we expect a programmer to use to run our program. But under this precondition, we want that this postcondition to be valid. So now that we have a formal specification, we can ask ourselves, does this program comply with the specification? And since we said that we want an addition, we can see that it does not. It failed to meet the specification. Okay? Why it failed to meet this specification? Because if we give x which is not 0, let's say x to be 2, the result will just be will just not account for these 2. It will be just y. Okay? Yes.
What do you think about the type constraints on the input? You know, if you program a language which doesn't have strong typing, should we think of those as preconditions as well that are separate in some sense?
No. So, thanks for the question. It helped me. It reminds me something I wanted to say. So, although I'm a formal method person, in this presentation I try to avoid as much formalism as possible, so I will try to be a bit informal. So in particular, I will use a bit precondition and postcondition in general, but I will also use types in some place. But what I want to give you is more like the overall feeling of how to do these things. Now, I will not go in the technical detail of different solutions. So you can think about these also as types, or you can think of adding the type constraint that will be the same. Any other question? Okay. So once we have the specification, we can try to see if our program guarantees it or not. And in general, we can have a different kind of specification. In this case, the specification is quite precise. It's only about the functional aspect. We don't say anything about how to compute it. We don't have, for instance, any requirement on the time that this function should take, or the memory that it uses, but it's quite precise on the functional specification. Now, this is a general idea that this is the basic. We need a formal specification, and then we can develop a tool to see if our program meets the specification or not, and maybe to help a designer to guarantee that the program meets the specification. Now, the formal method area is quite wide, and I tried to think about some way to compare the different formal methods, and I came up with this 3 direction. I think this will be useful a bit later in my talk when we will see a technique for differential privacy. Now, what I realize is that this 3D plot is good to just give the overall idea. When I will start to add point, is not clear in which direction we are going, but I will say this specifically later. So what are these 3 directions? So one of them is usability. So one of the reasons why formal method has not been widely used is that they don't come for free. No formal method comes for free. If you want just to have the same burden you have just by programming, then you cannot use any formal method. If you use formal method, you need to learn something new. You need to learn how to use them. But it's not something discrete. We have methods that are more usable, and methods that are more usable, and methods that are less usable. So this is certainly one of the directions. Another direction is the expressivity, is how far we can go in verifying our example. I showed you a tiny example before, but can we verify something like the application of the census? Can we really verify something big? Another direction is the granularity of the enforcement. Now, this is maybe not clear now, and it will become more clear later, is how far we go in the verification in the sense of how fine-grained we go in the verification. Are we verifying just an high-level algorithm, an high-level program, or we are verifying the whole software infrastructure? Because, of course, maybe we have something that is differentially private on paper or at the high level, but then maybe the implementation at the low level is not differentially private. So this is another direction that I think is important. Now, if we keep in mind this three directions, how can we guarantee that the program meets the specification? Now, I will try to look at three different directions in my talk. So the first one that was also the first one that came up in the differential privacy literature is trying to design a language or a system which guarantee the specification, the property of interest by design. So I write my program and I trust the developer of this programming language that I'm doing something that meets the specification. And this will be mainly the first part of my talk. Then in the second one, we will look at how to formally verify that the program meets the specification. And finally, I will also try to hint at testing that a program meets a specification. This is not usually considered a formal method because we don't have a guarantee which is 100%, but is a more statistical based guarantee where we can say that on a certain coverage of our code, we are quite convinced that the program meets the specification. And of course, I will try to look at these three approaches in the case of differential privacy. Okay. Any question? Yes.
Since you come from some more hardware background, how different are the methods that you use here than for like hardware verification?
That's a good question.
So, kind of statistical testing.
Yeah. So the first part I would say is very different because usually, actually no, I take it back. The first part is very similar to languages that have developed to specify hardware. So often they support some kind of verification. There is an whole branch of computer-supported design for hardware, and this is similar to the first part. The second, there has been some attempt, especially by Intel, for instance, in developing formal methods in the sense of formal verification for verifying hardware. And I think they are quite similar methods, but they, for instance, they don't care too much about probabilities, thing that is needed for differential privacy. So the technical details are quite different. And also testing is very well developed for hardware. The reality is that both for software and hardware, probably testing is what is more used in deployment of software or hardware. Yeah.
I have a question, always elementary, sorry.
Sure.
For point number one,
Yeah.
which is it like programming where there are a bunch of known languages and then for whatever you want to do, you might say, oh, this is, C++ will be good for doing it. But you say designing a language/system, do you have to design the language? How often are the formal methods people creating these languages?
Yeah, so that's exactly the job of formal methods people, designing new languages. So now, in general, I would say that maybe I say designing new languages, but what I really mean is designing new approaches. So not necessarily one specific language, but a family of languages that can support the specification. For instance, I was mentioning now hardware designing people, people that work on hardware design have developed languages that are specific for this task. And these are very different from C or Python or R, because they are domain specific to their need. So you have support to design circuit that you don't have in general programming. We can think also like statistical software as a domain specific in this sense.
So, following on Helen's question, just to understand the setup then, if this is a new language or system, can it then test other languages that are used? I mean, so in step 2, the program that's evaluated, does that have to be written in the same language, or
so,
other languages that can be?
Yeah, so that's a very good question. So in general, like we can think about these languages as independent from other application, but this is not the only approach. We could also think about synergy with other tools. So, for instance, we could imagine that I can write in my Python usual environment, and I use some primitive that has been designed with the other languages. So it doesn't need to be completely done in these new languages. It's not that we need to forget everything else.
So give us a name of some of the languages that formal.
Yeah, we will see in few slides. I mean, of course, the languages are not famous, I think, except in this community. But yes, I will give you some names. Any other question? Okay, so we focus on differential privacy. I think I don't need to go through the definition again. All of you now should know it. But one thing that I want to point out is that something that made me struggle a lot at the beginning when I entered this area of formal verification of differential privacy is that this definition talk about privacy, but then there is no mention to other property that we usually want. And I remember still one of the first discussion I had with Kobe saying, oh, but this program, blah, satisfies differential privacy. And Kobe said, not really, because it has no accuracy. So it was like a trivial example where the program was not computing anything interesting. And that made me understand that it's true that there are examples that respect this definition, but maybe...
Kobe, I don't think he would have said this.
Was I drinking something?
No. I think what you really meant is, actually you were drinking but a coffee. So I don't know if you have a strange reduction to coffees, but I think what you actually meant is, of course it respects this definition, but it's not something we usually want to consider. We don't even need to think about this kind of example, because it was almost useless. So this to say that I think in general, when I talk with you guys, you don't have only privacy in mind, but you have two other dimensions that are important to account. One is the accuracy of the analysis, and the other is the efficiency of the analysis. So for me, a program that runs in exponential time and is differentially private is perfectly fine, in the sense that it respects the previous definition. But on the other hand, this is probably useless. So in some sense, what I'm trying to say is that although we have a formal definition of privacy, in practice you, algorithm designer, often use also some definition of accuracy and efficiency that we need to consider. And I think in general we need to think about this as a correctness, not only privacy, but all these properties. Okay. Let me motivate one last time why we care about this in the context of privacy. So we may wonder if correctness matters for differential privacy. And we can just look at some of the things that went wrong for differential privacy and try to understand if we are at risk as a general, as other software. So I think one example that we use a lot to motivate our work is this example of a sparse vector. I think some of you have already seen this several times. I apologize for this.
Every time I get to read like one more of the examples on the slide.
Good. All right, so for the people that didn't see this slide before, so these are 6 variations of the sparse vector technique that appear somehow somewhere in the literature, and 3 of them are not differentially private. And the problem is that are small variation, and it's difficult to detect directly if they are differentially private or not. And I will come back on sparse vector later in my talk. But I think what I want to stress here is that these variations were not proposed by people that have no knowledge of privacy. These were proposed by people of the community, people that I trust, and I'm sure all of you. Sorry?
People you used to trust.
No, people that.
You're in one of the examples.
No, but that was the good one, yeah. But I think people that we should trust, but is just the problem that also people that can be trusted sometimes commit mistakes. It's a human committing mistakes, and so we need to take to try to avoid these mistakes, but the way to avoid it is not just by not trusting these people anymore, but trying to give them some way to support their claim. And so I think the work we are doing goes in this direction. Another example, I think some of you are familiar with this work by Ilya, who showed that a naive implementation of the Laplace mechanism is not differentially private. A naive implementation on using floating point number is not differentially private, and the reason is that we can use the irregularity of floating point number to reconstruct the secret. Now, his attack was on a small scale, but as Kobe said this week, we should be careful because even attack on the small scale, if we want, we can try to put them on a large scale. I don't think there was a real effort here to do it on a large scale, but I would not, I'm quite confident that this could be put on a large scale. And by the way, most of the implementation don't take care of addressing this attack, which I think tell us also something about people that are trying to deploy in differential privacy. Although we know that there are bad situations, they somehow, the cost that I was talking before, the cost of trying to address this situation is sometimes something that people don't want to afford. A last example of how things can go wrong is even if we implement things in the good way, we need to be careful with the usual problem that we have not only in differential privacy, but in many security applications, which are possible attack doing, for instance, to side channels. And for instance, some people made an attack on some of the languages I will discuss about based on timing attack. And this was, although some of them took care of high-level timing channel, at the low level, looking at the floating point implementation again, these people were able to do an attack. So we need to be careful. And this is also trying to give you the idea why having an end-to-end verified system, so from the high level, like from the high level specification, like we see here, to the more low level implementation, we need to take care of our property. Okay. Now, what are the challenges? And then I hopefully will answer Ellen's question. What are the challenges of verification for verification of differential privacy? I will sketch them here and then possibly come back later. So, in general, if we look at this definition, we have something that is a bit more involved than some other property verification people are used to work with. So the first complication is that when we reason about differential privacy, we reason about these two ideal world where we have two databases that differ in one individual. And this is not something baked in our algorithm, it's just the proof. So we need to reason about these two databases in some way. And we call this relational reasoning because we reason about the relation between two inputs. The two inputs differ in one individual. Then there is a lot of probabilistic reasoning, which set aside differential privacy from other settings. And then there is also a quantitative reasoning, because we know that we can think about this parameter of the definition of differential privacy as some kind of budget, and we need to reason about this. So we need a good decomposition of our problem that address these kind of properties. All right. So now let's see what people have done in this direction. Being a mini course, I will present a work by many people in the community. I hope I will give the good references, but please stop me if there is something unclear. So the first approach is designing a language which guarantees differential privacy by design. Now, I think one of the reasons why people got very excited about differential privacy, and I think we are all aware of that, is that it provides some compositional method to reason about application. So for instance, we have what in general we can call a sequential composition that say if we run multiple queries, then and each one of them is differentially private for some parameter of epsilon, then the overall process can be considered the sum of the parameter differentially private. Of course, this is the basic composition of differential privacy. We have a more advanced composition where I think we have seen some of them before in the week, where we have a better use of the parameter. But for my talk, I will not go into that. Now, another kind of composition that we have is what we often refer to as a parallel composition. And this is often, I think this term was used by Frank in his work on pink. But I think in general, this principle is used a lot in different analyses of differential privacy, and this idea that if we can somehow create a partition of the data, and then we run differentially private queries on each partition, then the overall process is mainly now we don't need to sum up the parameter, but we can just take the maximum of the parameter, or like in this case, if I use the same parameter, the overall process is just epsilon differentially private. Now, why these two compositions are useful? Because we can reason about privacy as a kind of budget, and this is very attractive. This is one of the reasons why I think differential privacy was is very attractive for several developers because we can reason about the consumption of privacy, and we have a mathematical calculus to do this based on this sum and max. Now, in this vision, we also have to be a bit careful because in general it's true that we can reason about privacy as a privacy budget, but we also need to think about some basic component and the privacy of this basic component. So composition is not everything. We need to start from somewhere. Now, I think one of the reasons also why this is attractive is that it avoids really reasoning about probabilities. Here there is no probabilistic reasoning in the idea of composing. The probabilistic reasoning is confined to the basic components, and this is very useful. And is a kind of general way of reasoning because we can use other composition, other definition of differential privacy, and still we can reason in this way. Yes?
So I joined in late, so maybe this is something you've covered before. But aren't you worried not so much about the budgeting, but also about the misuse of these concepts? For example, if I partition the data based on just a ridiculous rule, being close so far from the very first data point.
Sorry, yeah, I should have said that. Of course, when, yes.
Don't you need to verify these? Like the partition itself is independent of the data, all of these things that will make all of these theorems false.
Yeah, so that's a good point. Yeah, these are the basic components that I was saying in some sense. So when you do this partition, if you have a primitive for partition, you have to guarantee that the partitions are independent from the data. Now we are looking more at using this concept. Later I will go more in the boxes, yes. Any other question? Okay, so how can we use this idea? So I promise a bit more code, so let me try to go a bit into more code. Now, I want to show how we can use this principle on an example. This is an example I will use probably all along my talk. It's not, if you are looking for algorithmic, for good algorithmic idea, they are not here. This is a very simple example. It's just based on composition, as I was saying before. So what is this example? We want to mainly build a CDF of some data. And in general, we can think, when we program it, we can think that a way to do this is to take a list of buckets for which we want to compute the CDF of each bucket. What does it mean? We want to compute the number of records with value less than the element in the bucket. So for instance, in this case, we can say that the CDF of 20 is 0, CDF of 30 is 2, and CDF of 50 is 4. Okay, and build this. Now, how can we program this in an easy way? Here it is. So let me try to walk you through this code. So here I use is a bit less low level than the previous example because I use a bit more what nowadays we have available in many languages, which are some combinator to do filtering, to do composition, and so on. How can we interpret this? So the CDF first take two data. So it takes the database that I call DB and then the list of buckets for which we want to compute the CDF. And then it returns, sorry, this should be a list of int. Of course, I didn't verify my own code, and this is why there will be many typos. Sorry, this and return a list of counting mainly. Okay. Now, the way we do this is we iterate with a for loop through the list of buckets, and then for each element in the bucket, we take the database, we count by this command, we count how many elements in the data set are less than the element in the bucket. Now, how should we interpret this? Here we have two primitives. The primitive where, that is a filtering. It filters out the elements that are not less than the bucket. And then we use a count primitive, which count the resulting number of elements. And then we accumulate these in a list, as I said, and each one of these is a count, and then we return the list. Okay. Now, how can we build a private version of CDF? I will use a naive way. So the naive way is to do the CDF, build the list as before, and then add in Laplace noise to each element. Okay. These mainly use the idea of sequential composition, where we can guarantee that the overall process is differentially private, and if we add Laplace noise accordingly to epsilon over the number of buckets, we have that the overall process is epsilon differentially private. Okay? Is the algorithm clear? So I want to modify the code I showed you before that didn't have privacy to meet this specification. How can we do this? So one way to do this is exactly to add the Laplace noise to each count, so doing a count plus noise, and guarantee that we have this epsilon. Now, we want some system doing this for us, and this is what I will do next. But before going into that, I want to show you another kind of CDF that we can try to build using parallel composition. Okay? Parallel composition, again, we partition the element without looking at the data. It should not be based on the data, and then we run our differentially private queries on the partitioned data. So for instance, we can decide to partition our data accordingly to the buckets in different tables, and then build the CDF by summing up the result that we obtain. Okay, so for instance, if I do the CDF of 30, I have 2. And now for doing the CDF of 40, I will take these 2 and I will sum an additional element that come from the second table. For the third, I will do the sum of these 2 plus the additional element here. Okay? Okay. So how can we do this? We can do this, for instance, by this program, which has the same input and output as before, but now what we do before our for loop is to partition our data set, and now we assume that M is already the partitioned data set where we also do the count, and then for each element we sum, as I was saying before, we sum the previous element plus the additional count. Is this code okay with everybody? I'll give you 2 seconds. Okay. No question? All right. So now how we can do this private, we can add Laplace to each counter, and then we can sum the result with also this Laplace noise. Of course, here we will not have the same result as in the previous one because we are adding noise in a different way, but it's still an approximate CDF. So in particular here, we add the noise. to this counter, and then we sum up them. So the reason why I took this example is to show you that we could do a similar analysis using just sequential composition or using parallel composition. Okay. Now, how can we support this design? How can we support this reasoning about parallel and sequential composition? This was one of the first language that was proposed in this community for doing exactly this. It was the work by Frank on pink, and also I mentioned the work by Vitaly Shmatikov groups on iRavat. So Ellen, these are the two of the name you were asking about. Of course, these are known probably just in this community or in a community close to this. They are not used too much outside, but they try to achieve this goal, that is building applications that are private by design, differentially private by design.
Marco, just to get back to that question for a second. So like, these are sort of, algorithms with funny names. Like they are like built on top of familiar algorithms, right? They're like related to languages, like known languages with like extra commands for private.
Yeah, yeah.
So, like, one ideally would not have to like learn the new language from scratch. It would be like
that is a good point, and is actually my first point here. So pink is not really, and maybe this answer a bit to Frauke's question before. So pink is not designed in isolation, is designed inside the C#, which is a general purpose language. And we can think about it as an API. Actually, it's built on top of an API that people have designed before for data analysis, which is a link. This is or maybe more than data analysis, I would say like queries in the setting of SQL-like queries. So it was a language providing this primitive I showed you before, like where, count, and so on, to support the design of SQL kind of queries. And Frank extended it to address differential privacy. And it was a bit the first language that was designed, and it was designed with composition in mind. So the principle it provides is really this principle about composition. So to conclude this first part, I would like to show you how we can do our example in pink. So, and understand what are the features that pink provide to address the correctness issue. How pink help us design more correct applications. So this is how this program that I showed you before, the differentially private CDF based on sequential composition, would look like in pink. So if you are a pink programmer or a C# programmer, you would write something like this. I say something like this because I change a bit some part, but overall this is the general idea. And what pink provide are some new primitive like this pink agent budget that help with tracking the privacy budget. So these, for instance, create a new agent which is responsible of tracking the privacy budget, to which we give the budget. And from now on, every time we will perform a query, this agent will take care of checking if we have available budget, and if not, will tell us you don't have budget. We also need to provide mainly the data, the raw data to pink. Now, I put this part in this place, but usually this is maybe in a separate part where is the initialization of the application. So we create an agent that take care of the privacy budget and a pink wearable that takes care of the database. And then...
Just a question. So then you wouldn't pass around, at that point you wouldn't like pass around the agent variable. You just keep privdb would be the thing.
Yes. So
It's just like this one thing.
exactly. From now on, from now on, the only variable we will use is this privdb.
And behind the scenes, there's this agent that's tracking the budget consumption.
Exactly. So in particular, now you see that I write a program very similar to the one before, but where instead of using the database, we use exactly this private database that take care for us of the budgeting. And we also use a primitive noise count, which mainly perform the addition of Laplace noise, but it does this in a controlled way. And we call in general this transformation and this aggregation because the first one transformed the data set. We can think about it as changing the shape of the data set, for instance, by filtering out some element, we get a smaller table, and then with this we aggregate. And this is the first example. The second example can be written in a very similar way, where the part that changes is just the one below. We still have the pink agent for the budget. We have the private database. And what we change is just that we do a different kind of transformation, because now we do the partition. And then we do again the aggregation. Okay? Yes.
So what happens if you run out of privacy budget?
So if you run out of privacy budget, and we will see a bit later after the break, mainly the application tell you that you run out, and it will not answer any more queries. It will create an exception that say privacy budget over. Okay?
Maybe one other very elementary question. If I try to now access privdb not via like noisy count, but via like something non-private, like just count, will it also throw an error?
Yeah, exactly. That's the whole idea. So that once you have this kind of object, now this kind of object has an interface that allow only some kind of operation. So you cannot do a regular count. If you want, you need to do a noisy count. Okay. You cannot do. So since now this is a protected object, we need to guarantee that we do only operations that are safe. Okay. All right. So after the pause, I will look a little inside these boxes here. And then we will look at other methods.
So if there's a couple quick questions before the break, can I ask them now? Otherwise, we'll come back at 11. Perfect.
Yeah.
Cool.
Thanks.